Hi everyone. In this lecture, I'm going to discuss one example problem related on how to apply the relations that we have derived on the previous lectures to plot or to construct the shear and moment diagrams of beams problems or beam structures. Okay. In here, we have a cantilever beam. Okay. Let's call that this is joint A, this is joint B, and on this cantilever beam, distributed force is applied at the first half sections, okay, from A to C, and the magnitude of that distributed force is 8 kilonewton per meter. So that distributed force is uniform. And then a point load is applied at joint B, which is at the tip end of the cantilever beam, and is applied downward. Okay, and in here we would like to calculate the shear and the moment diagram, or we would like to plot or construct the shear and moment diagram using the 6 rules that we have discussed previously. Okay, so before plotting the diagrams, we have to first calculate the shear, no, the reactional supports, and I will leave this as an exercise for you, and I hope you have time to double check that the moment in here, the reactional moment, M at A, is 27 kilonewton meter, okay? And then the AY, okay, the reactional support in the Y direction is 18 kilonewton, okay? And there's no axial, there's no AX because there's no force in the horizontal direction, okay? So with these informations, okay, uh, by knowing the reactional supports and the applied forces on the beam, we can start applying the rules that we have derived in the previous lectures. Okay. So at point A, where x is equal to 0, right there, right? I'm going to apply the first rule, right? The fifth rule, which state that if we have a point force, right, that is applied upward, then then the shear diagram will jump outward. Okay, and in this case, it turns out I think it will be best if we can sketch this AY over here so that you guys don't confuse. So this is AY is equals to 18 kilonewton. Okay. So at point A, we have a reaction of force that is going upward, right? It's 18 kilonewton. So our shear diagram should start from, we jump upward, right? And the magnitude of that jump is also 18 kilonewton, okay? Right? So in here, we start with 18 kilonewton, okay? And then afterwards, we have, and let me use black to indicate the rules. Here is the fifth rule, right? And then afterwards, we have distributed force in here, okay? We have distributed force, right? 8 kilonewton meter, and we can calculate this area right here, and let's call that area as area 1. So A1 is 8 kilonewton per meter times 1.5 meter. So here we will obtain is equals to 12 kilonewton. Okay, and then by applying rule number 2, right, that the change in the shear diagrams, okay, between 2 points, in this case the points is A and C, okay, is equal to the negative, okay, of the area under the distributed force. The area under the distributed force is 12, so the change in here is A1, okay, because it's negative, then it's go downward, right? So in here, we know the value in here is 18 minus 12 is equal to 6. Okay, and then I will note that in here we apply rule number 2. Okay, and then by rule number 1 that state that the slope in the shear diagram is equal to the negative of the ordinate of the distributed force. Okay, so in here the distributed force is 8 kilonewton per meter. Okay, so the slope is going to be negative 8. Okay, so negative mean that it has to go down, right? It has to go downward linearly with a constant slope, which is negative 8. Okay, so in here I put that I apply rule number 1. Okay, and then on the section of the beam from C to B, there's nothing applied, so the shear diagram will remain constant, right? Okay, and it turns out that in here we have 6 and the applied load is 6 as well. Okay, right? That's our shear diagram. Okay, one thing that I would like to mention though, for example, if this beam is lengthened to point D, for example, okay, and P is still applied at B, okay, what will you expect of the shear diagrams from B to D? Well, it will go to 0 because if we apply rule number 5, right, if we have a point load that acts downward, then the shear diagram is going to jump downward. It means that it's going to jump from 6 kilonewton here, okay, to 0 because P is 6 kilonewton. Okay, but that's hypothetical because we don't have this extension of the beam right here. Okay. Alright, then let's see how we can apply the other rules to plot the moment equations. And in here we will apply rule number 3 and rule number 4. Okay, so we are going to first start with rule number actually we're going to apply rule number 3, 4 and 6. Okay, and we're going to start by applying rule number 6 first. Okay, so in here we see that we have MA, which is the reactional moment at A, and it's going counterclockwise. Okay, so we have learned that if we have a moment that's going counterclockwise, then we have the moment diagram will jump downward. Okay, so in here this is MA is equal to 27 kilonewton meter. Okay, so we start with MA is equal to 27 kilonewton per meter. Okay, and it's negative. It's negative. And afterwards, we can apply the rules number 4, okay, which state that the change in the moment diagram is equals to the area under the shear diagrams between the 2 points. And let's say that right now we evaluate the point A and point C, right, over here, and we try to calculate this area over here and call it A2. So A2 is the area under this shear diagram from A to C, okay, and A2 is the area of trapeziums. So we can use this 18 plus 6 divided by 2 times 1.5, okay, so this magnitude plus this magnitude divided by 2 times the height of the trapezium, which is 1.5. Okay, so in here we obtain that is equal to 18 kilonewton meter. Okay, and from the fourth rule we know that the change in the moment diagrams is equal to the positive of the area under the shear diagrams. So we know that in here this change right here is equal to A2, and it's go upward because it's positive, and the value right there is equals to negative 9, which is negative 27 plus 18. Okay? And we can apply the rule number 3 right now, which states that the slope in the moment diagram is equal to the ordinate of the shear diagram. Okay? And we can see that the ordinate of the shear diagram in here is 18, and in here is 6. Okay? And in here is a first order line, right? It's a first order polynomial. Then we pretty much sure that the moment diagrams is second order polynomial. However, we are not sure whether the shape looks like this or looks like the yellow line in here. Okay? And with the help of the third rule, we are going to be able to solve this. Okay, so note that in here, the slope of the moment diagram is equal to the ordinate of the shear diagram, right? The third rule. So the ordinate here is 18 at A, and the ordinate at C is 6. So the slope at A is larger than the slope at C. Okay, and let's evaluate this green curve. The slope at A of this green curve is smaller than the slope at C at this green curve. Okay. Meanwhile, on the yellow curve, the slope is larger at A compared to the slope at C. So most likely, the shape has to be close to the one that we sketched in yellow before. Okay. So it has to be, looks like this. So this is, the green curve is incorrect, so I'm going to erase it. Right? Okay, and then similar, we can apply the fourth rule again, stating that the change in the shear diagrams is equals to the area under the shear diagram. So we calculate this area of the shear diagram from C to B, and in here we call it area 3, right? And area 3 is just a rectangular, right? Which is 6 times 1.5 is equal to 9. Okay, so applying rule number 4, we know that the change in here, this is going to be A3, which is 9, which brings the diagram to 0. Okay, and B. Okay, and then we can apply rule number 3, which states that the slope in the moment diagram is equal to the ordinate of the shear diagram. Okay, and in here we know that the ordinate of the shear diagram is constant, 6, and is positive. Since it's constant, we know that the moment diagram is going to be linear, and it has positive slope, so it's going to go upward. Okay, so it's a linear line. Okay, so basically this is our moment diagram. Right, so you can see that in here, it seems like it's much easier to construct the shear and moment diagram using this rule, as long as we are able to calculate the area under the distributed force or the area under the shear diagram. Okay, and I think on the back of your textbook there is some help on calculating the area under certain shapes. Okay, because as you notice, I may not give you a problem with this uniformly distributed force. I may ask you a problem with of a beam that is subjected to triangularly distributed force. Okay. With that, I think it's enough for this lecture. Please let me know if you have any questions, and thank you for listening.